10,
let's go for main engine start.
6, 5, 4, 3, 2, 1, and booster ignition and liftoff of Space Shuttle Discovery, taking the space station to full power for full science.
Every civilization, from the first humans who gazed up at the night sky to the modern engineers soldering circuits onto spacecraft, has been haunted by the same question: how far can we go? So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here, and tell me in the comments where you are and what time it is right now. I always find it fascinating to see our little community scattered across the globe. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. It is a question older than writing, older than cities, older than the very myths we carved into stone. When early humans looked upward, they weren't just admiring the stars. They were confronting a mystery so overwhelming that it shaped our entire species. The night sky didn't just inspire wonder, it provoked restlessness. For tens of thousands of years, the cosmos was a place of gods and monsters, an unreachable dome painted above the world. The moon was a cold lantern. The planets were wandering lights. The Milky Way was a river of spirits. Everything above was fixed, eternal, divine. And yet, even then, something inside us resisted that boundary. Something whispered, what if we could go there? The first great explorers on Earth followed this same impulse. They built rafts to cross oceans they had never seen the other side of. They climbed mountains with nothing but instinct and curiosity. Human history is the story of expanding the horizon, and then realizing the horizon was never the limit at all. But when we finally set our sights on space, we met a frontier unlike any before. When explorers crossed oceans, the scale was daunting, but understandable. You could imagine sailing for months. You could picture a journey across land or sea. But space introduced a kind of distance that defied imagination, a kind of distance that seemed designed to humble us. To leave Earth entirely, a rocket must reach nearly 28,000 kilometers per hour just to enter orbit, more than 40,000 kilometers per hour to escape Earth's gravity completely. These numbers are absurd. They are unnatural. They shatter the limits of what life on Earth evolved for, and they mark the real beginning of humanity's journey into the cosmos. Because the truth is this: right now, in the entire 300,000-year history of our species, we have only taken our first fragile steps. Humans have traveled no farther than the moon, barely 1 light second away. Robots have gone further, yes, but even our fastest machines are crawling in comparison to the scale of the galaxy. If you shrank the Milky Way to the size of Earth, humanity hasn't traveled more than a single human hair's width. But before we talk about how far we can go, we must face the reality of how far we have gone. In 1961, Yuri Gagarin became the first human to escape the cradle. His journey lasted just 108 minutes, orbiting Earth at a height of only 300 kilometers. Less distance than many people travel by airplane in a day. And yet, that moment changed everything. Humanity had left the surface. We had crossed the invisible boundary that separated the earthbound from the spacefaring. Over the next decades, astronauts expanded that reach. Low Earth orbit, LEO, became our cosmic front yard. Geostationary orbit became the realm of satellites shaping modern life. The moon, 384,000 kilometers away, became a place where humans briefly walked, leaving footprints that will outlast every building on Earth. But after 1972, no human returned to the moon. Mars remained a distant dream, its red deserts taunting us with their silence. And beyond Mars, humans have never ventured. The irony is painful. The universe is open above us, and yet we are still confined to a tiny bubble. To understand how far we can travel right now, we must compare our abilities to the distances of the universe. Let's break it down. The moon, our greatest crewed achievement. Travel time, 3 days. Distance, 1.3 light seconds. Mars, our next major target. Travel time, current tech, 6 to 9 months. Distance, 3 to 22 light minutes. Jupiter. No human has gone, but we've sent probes. Travel time, robotic. 5 years. Distance, 35 to 50 light minutes. Pluto. New Horizons reached it after 9.5 years. Distance, 5.5 light hours. Interstellar space. Voyager 1 reached it after 35 years. Distance, 22 billion kilometers, or 21 light hours. Now let's compare this to the nearest star, Alpha Centauri. Distance, 437 light years. At Voyager's speed, that's over 70,000 years of travel. We have mastered hours of light distance. The universe demands years of light speed travel. Our reach is microscopic compared to the cosmic stage we stand on. The invisible wall. The greatest challenge in space travel right now isn't just distance, it's speed. Humans cannot travel faster than the rockets we build, and those rockets are slow compared to the vastness of space. Every second of light's journey is equal to 7.5 Earth circumferences, 300,000 kilometers, the space between stars, stretched over millions of years. Space is not empty, it is enormous. And our technology is still rooted in the physics of chemical fire. Think about that. We are trying to cross the galaxy using the same fundamental principle as the first fireworks invented in ancient China. More sophisticated, yes. More powerful, yes. But based on the same chemistry. That is like trying to circumnavigate Earth using only a rowboat. Right now, humans can realistically travel to low Earth orbit, to the Moon, potentially to Mars within the next decade, maybe to the outer planets robotically. And that's it. We cannot travel to the stars. We cannot reach other galaxies. We cannot even travel across our own solar system in a human lifetime, not with current technology. Our limitations are imposed by propulsion. Chemical rockets are slow and inefficient for interplanetary distances. Radiation. Space is a sea of deadly particles that our bodies are not built to withstand. Life support. Oxygen, water, food, and waste management for multi-year journeys remain unsolved challenges. Energy. Solar power becomes useless beyond Jupiter. Nuclear reactors are heavy and risky. Human fragility. Our bones, muscles, and minds deteriorate in deep space. Communication delay. At Mars, messages take up to 22 minutes each way. At Voyager, 21 hours. At another star, years. We are clever, determined, and ambitious, but the universe is unforgiving. We stand on a strange threshold. On one hand, we are the most advanced species the Earth has ever produced. We have walked on another world. We have machines exploring space beyond the sun's reach. We have telescopes that see galaxies older than the Earth itself. But on the other hand, we are astronomically limited. We have not left the solar system. We cannot reach even the nearest star. We are still prisoners of our own technology. Humanity is a newborn species staring out the window of its cradle into a storm of stars. We can see the universe. We can measure it. We can map it. But we cannot touch it. Not yet. So how far can we travel in space right now? The honest answer is both inspiring and heartbreaking. Humans can travel through only a tiny fraction of our own solar system. Robots can travel farther, but still only touch the outskirts of interstellar space. The stars remain beyond reach. In cosmic terms, we have barely moved. But here is the truth that matters most. Every step we take into space, every orbit, every probe, every rover, is the beginning of something much larger. Space travel is not measured in kilometers. It is measured in centuries of progress, generations of innovation, and the relentless refusing to give up that defines humanity. We are not limited by the universe. We are limited by the present. And the present is always temporary. Every era of human progress has been defined by the speeds we can reach. The horse carried us across continents. The steam engine carried us through nations. The airplane carried us over oceans. And the rocket, humanity's most violent, beautiful invention, carried us off the Earth entirely. Yet the transition from land to sky, from sky to orbit, and from orbit to deep space is not just a matter of going faster. It is a confrontation with the raw machinery of the universe itself, the physics that governs energy, gravity, momentum, and mass. To ask how fast we can travel right now is to ask how deeply we understand the rules of reality and how boldly we dare to challenge them. So before we ask, how far can we travel? We must understand the battlefield, the limits of propulsion, the barriers of velocity, and the true meaning of speed in the vast dark of space. Because the truth is simple and staggering. We are slow, painfully slow, slower than we realize, slower than our dreams demand, but not so slow that the stars are forever out of reach. Humanity today stands at the beginning of a long, steep slope, armed with technologies that push the boundaries of what seems possible. And to understand our cosmic potential, we must first walk through the engines, the physics, and the astonishing realities of traveling through space right now. Before a spacecraft can even think about traveling through the solar system, it first needs to escape Earth's gravitational embrace, a threshold we call escape velocity, 11.2 km/s, about 25,000 miles per hour. That number is the key to the universe. It is the minimum speed required to break free from Earth's gravity without falling back down. Every rocket ever built, Apollo, SpaceX Falcon, the Space Shuttle, the Soviet N-1, even the Saturn V, has had one job: hit escape velocity. Nothing more, nothing less. In reality, we don't launch rockets straight to that speed. We accelerate gradually, through stages, through the thinning air, through the layering of altitude, until momentum finally overtakes gravity. But here's the truth. Escape velocity is not traveling through space. It is simply unlocking the door. The moment a spacecraft clears that threshold, it can begin to build speed through orbital slingshots, interplanetary trajectories, and solar escape vectors. That's when our true travel speeds, our fastest machines, begin to reveal themselves. When people imagine how fast humans travel, they often look to rockets. But rockets aren't actually the fastest thing humans have ever ridden. The fastest speed any human has ever achieved was inside a tiny capsule falling toward Earth, returning from the Moon. NASA's Apollo 10, 39,197 km/h, 24,791 tilm. Human speed record. That means the fastest any person has ever moved is 0.0037% the speed of light. So small that even light would pass us 30,000 times faster. If light were a bullet, we would be a crawling insect. Does that mean humanity is slow? No. It means the universe is impossibly, almost mockingly, enormous. But human bodies themselves impose limits. Rapid acceleration can crush us. Excessive G-force can black us out. Our organs shift inside our ribcage. Our vision narrows. Blood struggles to circulate. We are fragile creatures swimming in a cosmic ocean built for giants. That is why robotic probes, not humans, hold the true speed records of our civilization. Humans cannot yet survive the forces required to travel at our fastest theoretical speeds. So we build machines that can, and some of those machines are astonishing. New Horizons, 2015 flyby of Pluto, 52,000 km/h, one of the fastest spacecraft ever launched. Voyager 1, currently in interstellar space, 61,200 km/h, still accelerating through gravity assists. Helios 2, 1976 solar probe, 252,792 km/h, record for 40 years. But then, the age of solar exploration arrived, and it shattered everything. Parker Solar Probe, current absolute speed record, 724,000 km/h as of 2024. Eventually expected to reach just 700,000 plus mph, 0.064% the speed of light. This spacecraft moves so fast that it could travel from New York to Tokyo in 50 seconds. It crosses Earth-Moon distance in under 6 hours. It orbits the Sun faster than any object ever built by humans. But even this speed, this unbelievable achievement, is still 1,560 times slower than light. So slow that crossing the Milky Way at this speed would take 1.5 billion years. We have built machines that skim the surface of a star, and yet the galaxy remains utterly indifferent. Space is not empty. It is ruled by physics that make high-speed travel brutally difficult. To accelerate something to high fractions of light speed requires immense energy. But energy is heavy, fuel is heavy, tanks are heavy, and weight slows everything. Chemical rockets, the ones that took us to the moon, have a fatal weakness. Their energy density is tiny. Hydrogen-oxygen fuel carries less power per kilogram than gasoline. To double your speed, you need exponentially more fuel. To reach 1% the speed of light, you would need millions of tons of fuel, a spacecraft bigger than a skyscraper, or propulsion physics we do not yet possess. This is why our fastest spacecraft gained speed not from fuel, but from gravity assists, slingshotting around planets. Solar wind, the sun's gravity well. We don't brute force our way through space. We glide, we fall, we borrow momentum from giants. We are clever, but still limited. Until we unlock new propulsion, fusion, antimatter, light sails, we will remain slow travelers in a fast universe. It is tempting to think, 700,000 km/h, that's extremely fast. It is. It's faster than any jet, rocket, missile, or human invention ever built. But the universe is not big, it is colossal, and the scale is unlike anything our minds evolved to understand. Let's do a simple comparison. Earth, Moon, 384,000 kilometers. Parker Solar Probe could reach it in 30 hours. Earth, Mars, closest, 56 million kilometers at our fastest, 1 month. Earth, Pluto, 5.9 billion kilometers at our fastest, 4 to 5 months. Impressive. But then, Earth, nearest star, Proxima Centauri, 4.24 light years. At Parker Solar Probe speeds, tunnel 6,600 years. Across the Milky Way, 100,000 light years. At Parker speed, 1.5 billion years. To the Andromeda Galaxy, 2.5 million light years. At Parker speed, 37 billion years. Suddenly, fast stops meaning anything. Our current speeds allow us to travel the solar system, but the galaxy, the other galaxies, those remain locked behind a wall of distance that mocks our engines. We have taken our first steps, but the marathon ahead stretches across cosmic eternity. It is the single defining constant of reality, 299,792 kilometers per second. Nothing can exceed it. Nothing with mass can reach it. It is the universe's speed limit, and also its greatest mystery. To travel, even 10% of light speed requires technology we do not yet possess. To travel 50% of light speed approaches science fiction. To travel 99% of light speed approaches physics-breaking territory, requiring exotic matter, extreme energy densities, near-perfect efficiency, materials that may not exist, an understanding of physics we currently lack. And yet, this is the speed necessary to cross the galaxy within a human lifetime. The gap between what we can do now and what is required is not just wide, it is astronomical. So what is our true limit, right now, today? We can travel the solar system, barely, slowly, carefully, but we can do it. We can send probes to Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, interstellar space with Voyager. We can send humans to low Earth orbit, the International Space Station, soon the Moon, eventually Mars, but beyond Mars, beyond the asteroid belt, beyond the Kuiper belt. Not with humans, not with our current technology. The solar system is our island. Everything beyond is ocean. To date, the farthest any human has ever been is 171 kilometers from Earth. Apollo 13 astronauts. That's it. 1 light second is 299,792 kilometers. Humans have traveled 1.3 light seconds from home. Meanwhile, Voyager 1, our farthest probe, has traveled 24 billion kilometer, 0.02 light years in nearly 50 years. The nearest star is 4.24 light years away. Even our most distant spacecraft is still 99.95% of the journey away from the closest star. We have crossed the street compared to the size of the continent. We have left the driveway compared to the size of the world. We have dipped our toes into the ocean compared to the size of the galaxy. And yet, it is a beginning. A small beginning, but a beginning. If humanity wants to explore new star systems, other habitable planets, galactic civilizations, interstellar networks, or the cosmic web itself, then our current speeds are not even close. We would need nuclear fusion rockets, antimatter engines, light sails powered by lasers, warp fields, or entirely new physics. We would need speeds of 10% light speed, 50% light speed, maybe even approaching light itself. Without those, interstellar travel is measured in millennia. But here is the secret. Humanity is not limited by imagination. It is limited by technology, and technology evolves. Once, crossing an ocean took months. Now it takes hours. Once, reaching the moon was impossible. Now we have done it. Once, traveling at 700,000 km/h was unthinkable. Now we have a spacecraft that does exactly that. The galaxy laughs at our speeds today. But what about tomorrow? This is humanity's speed story right now. We can escape Earth. We can cross the solar system. We can send machines to interstellar space. We can only send humans to the moon and near-Earth orbit. Our fastest robots are still 1,500x slower than light. And yet, every speed record we have broken was impossible once. Every frontier we have crossed was unreachable once. The universe is vast, beyond comprehension. But our ambition is also vast, beyond prediction. Right now, we are newborns on the cosmic scale, but newborns grow. And someday, if we survive long enough, we may cross distances that today seem absurd, traveling between stars, hopping between galaxies, exploring the cosmic web, reaching the universe's farthest shores. But before all of that, before warp drives, before interstellar colonization, before light-speed ambitions, we must first understand exactly how fast we can travel today. Not as a limitation, not as a defeat, but as a compass. Because humanity is not defined by where we are. We are defined by where we are going. From the moment humanity first looked up at the stars and whispered, "What's out there?" the universe has answered with silence. Cold, endless, unreachable. A dome of light so impossibly distant that even dreaming of touching them once bordered on madness. But humans are stubborn creatures. We do not accept silence. We build machines to speak for us. And in the great cosmic darkness, our machines have become the first emissaries of Earth. The scouts of a species still bound to its home world, yet daring enough to send its creations into the abyss. If humans are infants in the cosmic scale, then our spacecraft are the first crawling motions of a civilization learning how to stand. They are fragile, small, mortal, but they carry our dreams farther than our bodies can survive. So if you want to know how far we can travel through space right now, you must look not at people, but at the machines we have flung into the cosmic night. Because they go where we cannot. They endure what would kill us. And they carry our names farther than any human voice has ever reached. This is the story of our fastest messengers, the robotic explorers that define the true limits of our reach today. We begin with two small metallic twins launched in 1977 during the era of disco, cassette tapes, and rotary phones. Voyager 1 and Voyager 2 were built to last 5 years. They have lasted nearly 50. They were not built to go fast. They were built to go far, to take advantage of a once in 200 years gravitational alignment of the outer planets, Jupiter, Saturn, Uranus, Neptune. But nature gifted them with something extraordinary, the gravitational slingshot. When a spacecraft approaches a planet, it steals a tiny bit of that planet's orbital momentum, like grabbing onto a passing truck, letting it yank you forward, then letting go. Voyager did this 4 times. Each slingshot flung them faster and faster until Voyager 1 became the fastest escaping object in human history. 61,200 km/h, 38,000 km/h, 0.006% of the speed of light. It sounds small. It is small compared to the speed of light. But in human terms, it is astonishing. At that speed, you could cross the United States in 3 minutes. You could circle the globe in 24 minutes. You could reach the moon in 6 days. You could reach Pluto in 1,012 years. And so, in 2012, Voyager 1 did something no human-made object had ever done. It exited the solar system, not metaphorically, not symbolically, literally. It crossed the heliopause, the invisible boundary where the solar wind ends and interstellar space begins. For the first time in Earth's history, a creation of humanity left the sun's influence and stepped into the galaxy itself. A metal messenger, carrying a golden record, carrying greetings in 55 languages, carrying the heartbeat of Earth. Voyager shows us how far we can travel without human limitations. And yet, even at its current distance, over 24 billion kilometers away, it is still only 0.02 light-years from Earth. The nearest star is 4.24 light-years away. Voyager has traveled for nearly half a century, and it has completed 0.05% of the journey to another star. That is how vast space is. That is how slow our fastest probes still are. And that is why we must keep building faster ones. If Voyager was our first scout, New Horizons was our bullet. Launched in 2006, it didn't creep into space. It shot into it, faster than any spacecraft at launch, 536 km/h leaving Earth. It didn't orbit. It didn't slow down. It didn't linger. It raced relentlessly toward the outer solar system, toward Pluto, the world we once thought was just a frozen rock, until New Horizons showed us mountains of ice, atmospheres of haze, and plains the size of continents. New Horizons proved something important. We can send a small probe to Pluto in under 10 years. In cosmic terms, that is breathtaking. And with a Jupiter slingshot, its speed grew even more. 14 km/s, 50,000 ton-km/h, 0.005% of light speed. Still far from fast enough for interstellar travel, but fast enough to redefine what we consider reachable in one human lifetime. New Horizons is now drifting into the Kuiper Belt, photographing ancient worlds untouched for billions of years. It will eventually join Voyager in interstellar space. But its mission proves something Voyager could not. Speed can be engineered, not just borrowed. Humanity is learning. Slowly, but learning. Long before the Parker Solar Probe shattered records, there was Helios 2, a joint mission by NASA and West Germany launched in the 1970s. Its mission? To study the sun closer than any craft before. To do that, it fell inward toward the sun, using gravity, not fuel, to accelerate to speeds unheard of at the time. 252,792 km/h, 157,000 Tampa. This made Helios 2 the fastest object ever built by humans for 40 years. How? The sun's gravity. When you fall toward a star, you accelerate as if the universe itself is pushing you. Helios 2 revealed a secret humanity would later use. The path to high speed is not brute force, it is gravity. The sun is not just our star. It is the greatest accelerator humanity has ever discovered. A gravity well so deep that if you dive close to it, very close, you can reach speeds that no rocket could ever achieve by fuel alone. Helios 2 taught us the physics. The Parker Solar Probe exploited them. If speed had a throne, the Parker Solar Probe sits upon it. Launched in 2018, Parker is humanity's boldest, most extreme, most death-defying spacecraft. It is not orbiting the sun like Mercury. It is diving into it. Skimming the surface at distances so small, it would vaporize any unprotected object. The sun is unimaginable up close. 1 million degrees at the corona. Solar winds faster than bullets. Magnetic storms the size of Earth. Radiation that would kill a human instantly. Gravity so tremendous it bends space itself. And Parker is kissing that inferno. Why? Because the closer it gets, the faster gravity pulls it. Each orbit brings it closer. Each dive flings it faster. Each slingshot raises its velocity to new extremes. And so, Parker has broken speed record after speed record. 724,000 km/h, 450,000 mph, 0.064% the speed of light. That means New York, Los Angeles in 20 seconds, Earth, Moon in 5 hours, a full lap around Earth in 3 minutes. No other man-made object even comes close. This is the fastest humanity has ever traveled. This is our current limit. And even this speed, breathtaking as it is, would take 6,500 years to reach Proxima Centauri, 1.4 billion years to cross the Milky Way. The galaxy laughs at our achievements, yet celebrates them too. Because Parker shows something Voyager never could. Humanity is not only traveling far, humanity is learning how to travel fast. You may ask, if machines can go this fast, why can't we? The answer is harsh, simple, and biological. Machines are not. To reach Parker-like speeds a human would endure dozens of G-forces, lethal radiation, extreme temperature swings, micrometeoroid impacts at bullet speeds, months or years without resupply, cosmic rays that shred DNA, psychological collapse from isolation, oxygen, food, and pressure systems that cannot fail even once. Robotic probes don't need air, food, gravity, sleep, shelter, warmth, protection from radiation, emotional stability, long-term environmental support. They are simple, durable, replaceable, and they can survive where humans would die instantly. So for now, our machines define the true speed and distance limits of our species. Until we solve the biological constraints of human life, shielding, propulsion, acceleration tolerance, our own bodies will remain the slowest part of any journey. Together, Voyager, New Horizons, Helios, and Parker reveal 4 truths. Humans, not yet. Robotic probes, already there. We don't push probes fast. We let the planets and the sun pull them fast. We are thousands of times too slow. We are getting faster every decade. Helios, 250,000 km/h. Parker, 724,000 km/h. What comes next? Fusion drives? Antimatter engines? Light sails? The probes we build today are grandchildren of the probes we built 50 years ago. The probes we build 50 years from now will make Parker look like a toy. Humanity is learning the cosmic game. Slowly, painfully, but relentlessly. Imagine a future spacecraft with nuclear fusion propulsion, magnetic plasma drives, superconducting ion engines, light sails pushed by gigawatt lasers, antimatter bursts for acceleration, radiation-proof hulls, cryogenic sleep chambers. If that sounds like science fiction, remember, landing on the moon was once science fiction. Breaking escape velocity was once science fiction. Flying faster than sound was once science fiction. Touching the sun was once impossible. And yet, we did all of them. Humanity is slow today, but humanity is not finished. Every probe we send farther becomes a promise, a vow, a whisper to the universe. We are coming. Voyager carries a message. New Horizons carries a camera. Parker carries a shield glowing 1,000 degrees Celsius. But what they truly carry is something far more profound. Our courage. Our refusal to be trapped on one world. They are not just machines. They are extensions of human imagination. Small metallic seeds thrown into the dark soil of the galaxy. Someday, long after their power dies and their signals fall silent, they will still drift between the stars, carrying humanity's fingerprints across cosmic eternity. Long after our cities fall, long after Earth changes, long after the sun dies, Voyager will still be traveling. New Horizons will still be traveling. Parker will still be traveling. Our first footsteps in the universe will outlive us all. With humans, 1.3 light seconds, the distance reached during Apollo. With machines, 0.002 light years, Voyager's current distance. With speed, 0.0064% of light, Parker's solar dive. Compared to the size of the universe, these distances are small, but compared to every other species on Earth, they are infinite. We have touched interstellar space. We have visited every planet. We have raced around the sun at speeds unimaginable to our ancestors. We are not fast yet. We are not far yet. We are not powerful yet. But we are beginning, and beginnings matter. Every civilization has stared up at the night sky and felt the same stirring. Awe. The Milky Way, spilling across the darkness like powdered diamonds. The stars, glittering with the weight of untold histories, seem close enough to touch. And yet, we know they are not. They are unreachable. Not because of imagination, not because of curiosity, but because of the universe itself, the vast, indifferent expanse that separates us from the rest of creation. Right now, today, in 2025, humanity's ability to traverse that cosmic distance is painfully finite. Our fastest probes skim the solar system. Our human bodies remain tethered to Earth. This section is a journey through those barriers, through the limits imposed by distance, time, and the physics we have not yet bent to our will. Through the stark contrast between what seems close and what is truly far. It is tempting to measure space by the landmarks we know. The Moon, Mars, Jupiter, Saturn. These distances are staggering by human standards. Earth, Moon, 384,000 km, 1.3 light seconds. Earth, Mars, closest approach, 54.6 million kilometers, 3 light minutes. Earth, Jupiter, 628 million kilometers, 35 light minutes. Earth, Saturn, 1.2 billion kilometers, or 1.1 light hours. Yet compared to the galaxy, these numbers are laughably small. Consider the nearest star system, Proxima Centauri, 4.24 light-years away. In kilometers, that is 40 trillion kilometers, 40,000 kilometers. Voyager 1. Humanity's farthest traveling probe would take over 6,600 years to reach it at its current speed. The difference between the solar system and the stars is not merely farther, it is a quantum leap in scale. We often talk about speed in isolation. We can travel at 700,000 km/h. That sounds fast. It is fast. But speed, without context, is meaningless in the universe. The Milky Way alone is 100,000 light-years across. The nearest galaxy, Andromeda, is 2.5 million light-years away. Even at the Parker Solar Probe's record-breaking velocity of 724,000 km/h, it would take 1.5 billion years to cross the Milky Way, 37 billion years to reach Andromeda, and this is with a machine capable of surviving temperatures near the Sun, radiation stronger than Earth's magnetosphere can handle, and speeds unimaginable to our ancestors. Time, more than distance, is the real barrier. Traveling today is not just slow, it is a confrontation with human impatience and mortality. Even if a probe could maintain its speed forever, crossing the stars within a human lifetime is currently impossible. The universe has built in an eternal gap between us and its other realms. Space is not merely large, it is energetically cruel. To travel faster requires exponentially more energy. To carry fuel adds mass, which requires yet more energy. To accelerate a human to even a small fraction of light speed could annihilate the body under G-forces that no living creature can endure. Consider chemical rockets, the backbone of modern human spaceflight. They work through simple combustion, fuel plus oxidizer, burning in controlled explosions. The Saturn V, which sent humans to the Moon, produced 34.5 million newtons of thrust. It reached escape velocity, 11.2 km/s. But in cosmic terms, that is still 0.0037% of light speed. Even our fastest probe, the Parker Solar Probe, achieved its velocity not by brute force, but by falling into the Sun's gravity well. The takeaway: energy requirements scale with distance and speed. Even our fastest probe, the Parker Solar Probe, achieved its velocity not by brute force, but by falling into the Sun's gravity well. The takeaway: energy requirements scale with distance and speed. To move beyond the solar system within a human lifespan would require propulsion methods that remain theoretical today. Nuclear fusion engines, matter-antimatter drives, light sails propelled by enormous lasers, possibly even harnessing the energy of black holes or gravitational waves. Until we develop these, speed is limited by fuel, mass, and the physical limits of humans. Even if we could accelerate to significant fractions of light speed, humans face another hurdle: survival over long durations. Consider a journey to Proxima Centauri. At 10% of light speed, 42 years. At 50% of light speed, 8.5 years. At 90% of light speed, 4.7 years. The journey itself presents problems beyond propulsion. Food, water, and oxygen must be maintained over years in a sealed environment. Radiation exposure outside the protective magnetosphere of Earth or Sun is lethal over time. Psychological strain from isolation, confinement, and distance from Earth is unprecedented. Micrometeoroids at high velocities become deadly projectiles. Even today's International Space Station astronauts face profound mental and physical stress after months in low Earth orbit. A human journey beyond the solar system would require technologies to sustain life decades at a time, shield from cosmic radiation, and provide psychological support for a crew traveling into the cosmic void. Distance in space is not just a challenge for propulsion, it is a challenge for communication. Even today, with robotic probes near Pluto, signals take hours to travel. Earth, Mars, 3 to 22 minutes one way. Earth, Saturn, 1.2 hours one way. Earth, Pluto, 4.5 hours one way. Imagine a probe in interstellar space, 4.24 light-years away. A message from Proxima Centauri would take 4.24 years to arrive. A response from Earth, another 4.24 years. Humans could not operate in real time. We would be interstellar ghosts, unable to intervene, correct, or respond during critical moments. This is why autonomous decision-making and artificial intelligence are not optional. They are essential for survival in deep space. Distance and speed are not the only obstacles. Space travel is also constrained by the invisible forces that shape the cosmos. Gravity wells are one of the universe's primary constraints. The deeper the well, the harder it is to escape. Escaping Earth requires 11.2 km/s. Escaping Jupiter's gravity requires 60 km/s. Escaping the Sun itself requires 42 km/s from Earth orbit. Even small planets, asteroids, and moons can alter trajectories. Every journey through the solar system is a dance of acceleration, deceleration, and slingshots. The faster we want to go, the more careful the choreography must be. Space is not empty. It is a web of invisible forces that both aid and impede our travel. All these barriers converge at the ultimate limit, the speed of light. Nothing with mass can reach it. Energy required to approach it grows exponentially. Time dilation becomes extreme. Time slows for the traveler relative to Earth. Even photons, massless particles, cannot exceed it. Our fastest probes are still only 0.064% of light speed. To reach even 1% of light speed with humans on board is beyond current chemical or nuclear propulsion. To reach 10% or 50% of light speed remains theoretical, demanding technologies we have not yet discovered. The universe sets these rules not as a suggestion, but as a law. Speed, like distance, is a cosmic boundary we have not yet crossed. And yet, perspective is everything. While the stars may seem unreachable, our probes have already escaped the Sun, skirted planets at incredible speeds, and traveled billions of kilometers beyond Earth. We have sent human bodies to the Moon. We have mapped the solar system. We have glimpsed Pluto up close. We have flown closer to the Sun than Mercury. From that perspective, humanity is not entirely powerless. We are the first species in history to consciously step into space, to send messages to other worlds, to push metallic bodies into the void with intent, purpose, and planning. Every probe, every spacecraft, every mission is a demonstration of how far human ingenuity can carry us today. We are close, and yet we are infinitesimal. In a lifetime, a probe can travel across the solar system. In the lifetime of a star, it cannot reach the nearest star system. In the lifespan of a galaxy, humans remain tethered to one small planet, orbiting one ordinary star. This is the paradox of space travel today. Our technology expands our reach, but the cosmos expands faster. It humbles, it terrifies, it inspires. We are infinitesimal, yet determined, small, yet ambitious, limited, yet reaching. So, how far can we travel through space right now? Humans, low Earth orbit, the Moon, and soon Mars. Probes, solar system, heliopause, beginning of interstellar space. Speed, fractions of a percent of light speed at best. Technology, capable, remarkable, yet still inadequate for interstellar colonization. The solar system is our playground. The stars are our dream. Every probe, every rocket, every spacecraft is a bridge between those realms. A tiny spark that says, we will go farther, we will reach further, we will touch the stars. We are limited, we are slow, we are fragile, and yet we are beginning. Because beginnings are not the end. They are the first proof that the impossible may one day be inevitable. Every civilization that has dared to look beyond its home has asked the same question. How far can we go? It is a question that humbles and terrifies, that inspires both wonder and dread. Today, that question has a more tangible answer than ever before. The Moon is no longer a distant dream. It is a destination we have reached. Mars is no longer a fantasy. It is within reach, a red beacon in the night sky that calls humanity forward. Asteroids drift silently between worlds, mysterious relics of the early solar system, each one a potential stepping stone to further exploration, or a cautionary reminder of our fragility. And yet, the further we go, the more apparent the limits of our technology and biology become. Mars has fascinated humanity for centuries. Its red hue, visible with the naked eye, has inspired myths, legends, and now scientific ambitions. To consider traveling there today, we must face the facts. Distance. Earth to Mars varies between 54.6 million kilometers, closest approach, to 401 million kilometers, farthest distance. Travel time. Using current chemical rockets, a one-way journey takes 6 to 9 months, depending on the orbital alignment. Orbital mechanics. Space agencies plan missions during launch windows, when Earth and Mars are favorably aligned, a cycle that occurs roughly every 26 months. Even this seemingly simple journey is fraught with challenges. Radiation exposure. Unlike Earth, Mars has no global magnetic field to protect explorers. Cosmic rays and solar radiation bombard the surface. Extended missions expose humans to doses far beyond what is safe on Earth. Life support, oxygen, water, and food must be generated or transported. Closed-loop life support systems are complex and prone to failure. Psychological factors, a journey of months, confined in a small spacecraft with no possibility of emergency return, places immense mental stress on crew members. Landing and ascent. Mars's gravity is weaker than Earth's, 38%, but landing a heavy spacecraft safely is technologically demanding. Returning to orbit requires additional fuel, precise timing, and engineering that has yet to be fully tested with humans. Yet, despite these hurdles, Mars is not unreachable. NASA's Artemis program, SpaceX's Starship ambitions, and international collaborations aim to establish the first human presence on the red planet within the next few decades. Mars is the first test of humanity's ability to survive months in deep space, to operate far from Earth's safety net, and to maintain the physical and psychological health of astronauts in extreme conditions. While Mars looms as a distant prize, the Moon is a closer, immediate goal. Humans have set foot there, yes, but that was decades ago, in a different era of technology, politics, and ambition. The Moon today represents the next step in operational experience for long-term space travel. Distance, 384,000 kilometers, 1.3 light seconds. Travel time, around 3 days using modern rockets. Challenges, surface conditions, dust, radiation, and microgravity. Why return? Training for Mars. A lunar base allows testing life support, habitats, and long-duration human missions in a controlled, nearby environment. Resource utilization. The Moon may harbor water ice in permanently shadowed craters, providing fuel and oxygen for future missions. Scientific discovery. Understanding lunar geology informs planetary science and the history of the solar system. The Moon is humanity's first permanent foothold beyond Earth. It is a laboratory, a proving ground, and a launch pad. Without mastering the Moon, Mars remains a distant dream. Between Mars and Jupiter lies a region often overlooked but scientifically critical: the asteroid belt. Millions of rocky bodies orbit the Sun, ranging from dust-sized particles to dwarf planets like Ceres. Many are rich in metals and volatile compounds, water, carbon, rare elements. Some are remnants from the early solar system, preserved for billions of years. Asteroids are important for two reasons. 1. Scientific value. Studying them reveals clues about planetary formation and the conditions that allowed life to emerge on Earth. 2. Resource potential. They may provide the raw materials for deep space colonies, eliminating the need to launch heavy supplies from Earth. However, traveling to the asteroid belt is not simple. Distance: 3.5 AU from the Sun, 1 AU Earth-Sun distance. Travel time: 3 years using current propulsion. Navigation: the gravitational influence of Mars, Jupiter, and other asteroids requires precise calculations to avoid collisions. Radiation: deep space exposure is prolonged, with no protection from magnetic fields. Asteroids could be humanity's stepping stones into the outer solar system. But to use them safely, we must master long-duration human spaceflight, precise orbital navigation, and autonomous spacecraft systems. Jupiter, Saturn, Uranus, Neptune, the outer giants. Distance: 628 million kilometers to 4.5 billion kilometers from Earth. Travel time: 113 years with chemical propulsion. Gravity: enormous, creating both hazards and opportunities. The gas giants are not destinations for human colonization. Their hostile atmospheres and crushing pressures make landing impossible. But they are critical for other reasons. Gravitational slingshots. NASA's Voyager, Galileo, and Juno missions used planetary gravity to accelerate spacecraft, extending humanity's reach. Scientific discovery. Studying their moons, Europa, Titan, Enceladus, could reveal signs of life or resources for future colonists. Reaching the outer planets is feasible robotically, but human missions remain decades away, limited by life support, propulsion, and radiation protection. Beyond Neptune lies the Kuiper Belt, a frozen wasteland of icy bodies, Pluto, Makemake, Haumea, and countless smaller objects. Distance: 3050 AU, 4.5 to 7.5 billion kilometers from Earth. Travel time: 10-20 years using current spacecraft. New Horizons flyby of Pluto in 2015 was humanity's first close encounter with this region. It revealed a world of mountains, ice plains, and nitrogen glaciers, far more dynamic than imagined. Kuiper Belt exploration represents the outer edge of our current reach. It is the boundary between the near solar system and the unexplored interstellar frontier. Human missions here are impossible today. Even unmanned probes take decades to arrive. Yet, studying the Kuiper Belt prepares humanity for future interstellar travel, for understanding long-term navigation, communication, and resource utilization in deep space. Traveling in the solar system is not just a matter of distance and time. Space is filled with invisible hazards. Radiation comes from the Sun, solar flares and coronal mass ejections, galactic cosmic rays, high-energy particles from outside the solar system, trapped radiation belts, Van Allen belts around Earth and Jupiter. Exposure can increase cancer risk, damage nervous systems, kill cells essential for organ function, interfere with electronics on spacecraft. Protecting humans requires shielding, magnetic fields, or underground habitats, none of which are fully tested in deep space. Radiation remains one of the most formidable barriers to long-duration human travel beyond Earth orbit. Even if we survive distance, time, and radiation, we must survive ourselves. Life support systems in spacecraft must provide oxygen, Water, food, waste recycling, temperature regulation, pressure control. The International Space Station proves this is possible for months at a time, but Mars and the asteroid belt require years-long reliability. Closed-loop systems are essential. Plants can produce oxygen and food. Water must be recycled repeatedly. Microbes can assist in waste breakdown and soil enrichment. Failures are catastrophic. One leak, one system malfunction, and the mission could end in disaster. Human survival in deep space is as much an engineering problem as it is a biological one. Current rockets rely primarily on chemical propulsion, effective for reaching orbit, the Moon and Mars, limited in speed and efficiency for long distances. Fuel mass grows exponentially with desired velocity. Alternative propulsion methods are under study. Nuclear thermal rockets, faster than chemical, can shorten Mars trips. Ion engines, extremely efficient, can operate for years but provide low acceleration. Solar sails use sunlight or lasers to accelerate over long distances. Fusion engines, theoretical, could achieve fractions of light speed. Until these technologies mature, humanity remains slow-moving, fragile, and tethered to the sun. Traveling far is not enough. We must know where we are and stay in touch. Delays. Signals to Mars take 3 to 22 minutes, to Saturn 1.2 hours, to Pluto 4.5 hours. Navigation. Minor errors can accumulate, requiring course corrections decades apart. Autonomy. Deep space missions increasingly rely on AI to adjust trajectory, monitor systems, and respond to emergencies. Communication delays mean humans cannot pilot spacecraft in real time. Autonomy is essential. So, how far can humanity travel right now? Humans. Low Earth orbit, 400 kilometers, ISS. Moon, 384,000 km. Mars. Reachable in 6 to 9 months with chemical rockets. Robots. Voyager. 1, 0.002 light-years. New Horizons. Kuiper Belt. 4 to 7 billion kilometers. Parker Solar Probe. 0.064% of light speed. The solar system is the limit. Interstellar travel remains theoretical, and yet these limitations tell a story not of failure, but of potential. Mars is within reach. The Moon is a laboratory. Asteroids can be resources. Outer planets are laboratories for science and propulsion experiments. Kuiper Belt exploration teaches long-term navigation. Humanity has a solar system to explore, and every probe, rocket, and mission expands the horizon further. The distances are immense. The challenges are severe. The risks are high. And yet we have already crossed boundaries once thought impossible. Orbiting the Earth, landing on the Moon, flying past planets, entering interstellar space. Today's limits are tomorrow's stepping stones. Our reach may be small relative to the galaxy, but it is enormous relative to Earth-bound life. Every human in space, every robotic probe, every launch is proof that we are leaving our cradle. The solar system is ours to explore. The stars await. Every age of human history has been defined by its reach. The first humans ventured beyond their caves to hunt, to gather, to cross rivers and mountains. The first sailors navigated past familiar coasts, discovering continents that had been invisible to their ancestors. The first astronomers mapped the stars, realizing that the heavens were a vast expanse, ordered but immense. Today, humanity faces a new frontier, interstellar space. Our feet are still on Earth, our machines still skimming the edges of the sun's influence, yet our imagination reaches farther than ever before. The question is no longer, can we reach the stars? The question is, how could we? In this section, we explore the possibilities, the physics, and the technologies that might one day allow humans to move beyond the solar system, bridging the vast distances that today make such journeys inconceivable. To grasp the magnitude of interstellar travel, we must confront the numbers. Nearest star, Proxima Centauri, 424 light-years away. Milky Way diameter, 100,000 light-years. Nearest large galaxy, Andromeda, 2.5 million light-years away. Current spacecraft, like Voyager 1, travel at 17 km/s. At that speed, reaching Proxima Centauri would take over 70,000 years. The problem is simple in theory. The universe is vast. The problem is impossible in practice. Human lifespans are short, chemical rockets are slow, and energy requirements grow exponentially with speed. To travel even a fraction of the distance to the stars, humanity must reinvent propulsion. Today's rockets rely almost entirely on chemical propulsion. They are excellent for lifting payloads into orbit. They are adequate for traveling to the Moon or Mars. They are insufficient for interstellar travel. The limitation is energy density. Chemical fuel releases only so much energy per kilogram. To reach even 10% of light speed, a spacecraft would require massive amounts of fuel, far beyond what could be practically carried. Even advanced nuclear thermal rockets, the next step in propulsion, would reduce travel time to Mars or Jupiter, but would still be hopelessly slow for interstellar distances. The conclusion is stark. We need propulsion methods that go beyond anything humanity has ever built. Ion engines, like those used on the Dawn spacecraft, represent one approach to efficient travel. They expel ions at high velocity, generating small but continuous thrust, extremely fuel efficient, allowing spacecraft to accelerate for years. Low acceleration means patience is essential. Reaching outer planets can take decades. Ion engines cannot deliver humans to other stars within a lifetime, but they show a principle. Sustained, low-thrust propulsion can eventually achieve incredible velocities. For robotic missions, ion engines offer a path to the edge of the solar system and beyond. For humans, they illustrate the principle that speed is not always instantaneous. Endurance matters. Nuclear energy provides a dramatic increase in potential speed. Fission rockets split atoms to release energy, producing more thrust than chemical rockets. Fusion rockets fuse atoms, potentially achieving up to 10% of light speed. Fusion, the process that powers the sun, holds enormous promise. Hydrogen isotopes fuse into helium, releasing vast energy. Theoretically, fusion propulsion could shorten a trip to Proxima Centauri to decades rather than millennia. Challenges remain: initiating and sustaining fusion, converting energy to thrust, containing radiation. Nuclear propulsion represents the first technology that could make interstellar travel conceivable within a human lifetime, a bridge from imagination to reality. If fuel is the limiting factor, why carry it at all? Light sails offer an elegant solution. Harness energy already in space. Ultra-thin reflective sails are pushed by sunlight or powerful lasers. Acceleration is slow but continuous. No onboard fuel is needed, drastically reducing mass. Projects like Breakthrough Starshot aim to send tiny probes to Proxima Centauri at 20% of light speed, reaching the nearest stars in 20 years. For humans, scaling up light sails is enormously challenging. Maintaining structural integrity of a massive sail, shielding humans from intense acceleration and cosmic radiation, generating the laser power required for propulsion. Yet the principle is sound. Light, the fastest entity in the universe, could carry humanity forward. Antimatter represents the ultimate energy source. When matter and antimatter collide, they annihilate, converting 100% of mass into energy. By comparison, chemical reactions convert 0.01% of mass into usable energy. A small amount of antimatter could theoretically propel a spacecraft to relativistic speeds, approaching the speed of light. Challenges. Producing antimatter is extremely difficult and expensive. Storing it safely without annihilation is beyond current technology. Controlling a reaction for propulsion is unknown. Yet, if mastered, antimatter could unlock the stars in ways we cannot yet fully imagine. Even if we could achieve 90% of light speed, we would face the strange effects of relativity. Time slows down for the traveler relative to those left on Earth. A trip to Proxima Centauri at 90% of light speed could take 4.7 years ship time. But Earth would experience over 4.7 years as well. This is a profound shift in perspective. Interstellar travel is not just a technical challenge, it is a temporal one. Astronauts would age slower than those on Earth, creating relativistic isolation that adds psychological and social challenges. Even at high speeds, the space between stars is not empty. Hydrogen atoms in interstellar space become deadly at near light speeds. Tiny dust particles can destroy spacecraft traveling at 50–90% of light speed. Radiation hazards increase dramatically with velocity. Protecting humans and instruments requires shields, magnetic fields, or sacrificial layers, none of which have been tested at relativistic speeds. The universe is not merely vast, it is actively hostile to travelers moving at incredible velocities. Before humans attempt interstellar travel, robots must go first. Voyager 1 and 2 have entered interstellar space, giving us a taste of what lies beyond the Sun's influence. Breakthrough Starshot envisions microprobes reaching Alpha Centauri in decades. Future robotic explorers will map radiation, gravitational anomalies, and interstellar dust. These missions are humanity's first footprints outside the solar system, testing technology, navigation, and survival strategies for the journey ahead. Even if propulsion, radiation, and energy are solved, human psychology remains a limit. Isolation, years or decades in a confined spacecraft, communication delays, months or years with Earth, relativistic disconnection. Time on Earth moves faster than on board. Interstellar travel will require new social structures, mental health protocols, and autonomy. Human survival is not only about engineering, it is about resilience, adaptability, and willpower. Interstellar travel is not an individual challenge. It is a civilization-level effort. Constructing fusion engines or antimatter reactors, building space habitats capable of decades-long missions, launching and guiding interstellar probes with extreme precision, generating power for laser-driven light sails. These are not incremental improvements. They are leaps in engineering, energy management, and global collaboration. Humanity has done extraordinary things before, building pyramids, traversing oceans, landing on the moon. Interstellar travel is the next leap, requiring vision, patience, and ambition on a planetary scale. Why attempt the impossible? Curiosity. Humanity has always sought to know what lies beyond. Survival. Expanding beyond Earth reduces existential risk. Innovation. The technologies developed for interstellar travel transform life on Earth. Inspiration. The dream of reaching the stars unites generations. The universe is vast, we are small, and yet, our dreams are vast too. Every probe, every engine, every laser, every plan is a statement that we will not be bound by gravity or distance. Imagine a human mission to Proxima Centauri. Speed, 50% of light speed, theoretical with fusion or antimatter. Duration, 8.5 years ship time, 8.5 years Earth time. Crew, highly trained, psychologically resilient, multi-generational perhaps. Habitat, radiation shielded, self-sustaining, AI assisted. It is a dream today. It is plausible tomorrow if humanity invests in energy, propulsion, and life support technologies. Even reaching this level represents a transformative leap in human capability, marking the first chapter in the story of interstellar civilization. At light speed or near it, the distances we thought trivial become staggering. Earth to Mars, months. Earth to Jupiter, years. Earth to Proxima Centauri, decades. Earth to Andromeda, millions of years. Even in our best dreams, we are small, fragile, and finite. Yet, the potential to explore, to send probes, to dream, and eventually to travel, remains one of humanity's defining qualities. Our limitations are not permanent. They are challenges to overcome, barriers to push against, milestones on the way to the stars. Today, our spacecraft skim the edges of the sun's influence. Today, humans remain Earth-bound, tantalizingly close to Mars and the Moon. Today, interstellar travel exists only in theory, speculation, and imagination. Yet every journey begins somewhere. Every rocket fired, every probe launched, Every calculation solved is a step toward a future where humanity reaches the stars. Light speed may remain unreachable. Distances may remain vast. Time may remain cruel. And yet, we continue. We reach. We imagine. Because this is the essence of being human, to confront the impossible and to dare to go farther than we ever have before. Every dream of reaching the stars is accompanied by a shadow, the knowledge that space is not kind to the unprepared. For centuries, humans have looked to the night sky and imagined distant worlds. Yet the universe remains vast, indifferent, and sometimes hostile. To venture beyond our solar system, even at fractions of light speed, is to confront not only distance, but a series of obstacles that challenge physics, biology, and psychology. In this section, we explore these hazards in detail, examining how they shape the possibilities of interstellar travel and what humanity must overcome to survive among the stars. Space is filled with invisible particles that carry immense energy. Even within the relatively safe environment of low Earth orbit, astronauts are exposed to more radiation than on Earth. But in deep space, the threats multiply. Galactic cosmic rays, GCRs, high-energy particles traveling near the speed of light, originating from supernovae and other cataclysmic events. They can penetrate spacecraft, damage DNA, and interfere with electronics. Solar particle events, SPEs. Eruptions from the sun send bursts of protons and heavier particles through the solar system. These storms can be deadly without sufficient shielding. Secondary radiation. When high-energy particles strike spacecraft materials, they create secondary radiation, further increasing exposure. The consequences for humans are severe. Increased risk of cancer and other chronic diseases. Damage to the central nervous system, impairing cognition and coordination. Acute radiation sickness during intense solar events. For spacecraft traveling at 10 to 50% of light speed, the problem intensifies. Particles striking the ship generate additional energy, potentially turning harmless hydrogen atoms into lethal bullets. Space is not empty. Even in interstellar space, tiny particles, micrometeoroids, and cosmic dust travel at incredible velocities relative to a spacecraft. At near light speeds, a particle the size of a grain of sand can puncture hulls, destroy instruments, or vaporize on impact, releasing plasma and shockwaves. Shielding is difficult. Thick armor adds mass, reducing acceleration. Magnetic or electrostatic shields are theoretical but promising, using fields to deflect charged particles. Whipple shields, layers of material that absorb impacts, have been tested on satellites, but not at relativistic speeds. Traveling faster increases risk exponentially. A journey to the nearest stars may be safe for tiny probes, but humans will require advanced protection or sacrificial shields. Even if we survive radiation and dust, we must know where we are and where we are going. The nearest star is 4.24 light-years away. Small errors in trajectory, amplified over millions of kilometers, can result in missing a target entirely. Navigation in interstellar space requires precision star tracking, using distant stars as reference points, autonomous course corrections, AI systems capable of calculating trajectory adjustments without real-time communication, redundancy, multiple instruments to account for failures or miscalculations. Unlike near-Earth travel, there is no GPS or ground control. The spacecraft must be self-reliant, capable of measuring and correcting its path over decades. Traveling at significant fractions of light speed introduces strange and counterintuitive effects. Time dilation. For travelers, time slows relative to Earth. A journey to Proxima Centauri at 80% light speed might take 5 years ship time, but 6.5 years would pass on Earth. Relativistic mass increase. As velocity approaches light speed, energy requirements increase exponentially, making acceleration increasingly difficult. Aberration of light. Stars appear to shift position, moving toward the forward direction of travel, affecting navigation and perception. These effects are more than curiosities. They directly influence mission planning, propulsion requirements, and human experience. A mission to the stars is not just a technical challenge. It is a journey through altered space-time. Even traveling to the nearest stars, communication becomes a challenge. At Proxima Centauri, one-way signals take 4.24 years. At 10% of light speed, a probe cannot receive real-time guidance from Earth. Autonomous systems must operate independently, making decisions, correcting errors, and responding to emergencies without human input. Communication delays redefine command structures. For interstellar missions, Earth becomes a distant observer, unable to intervene in real time. Human crews must trust their own judgment and AI systems, knowing that assistance may never arrive. Assuming humans can survive radiation, dust, and navigation hazards, they still face the challenge of surviving themselves. A multi-decade journey requires oxygen recycling, water purification and reuse, food production or storage for decades, waste recycling systems, psychological support for long-term confinement. The ISS demonstrates that humans can live for months in microgravity, but years or decades in deep space is a different magnitude entirely. Closed-loop systems must function without resupply. Redundancy is critical. One failure could be fatal. Mental health becomes as important as physical health. Long-duration life support is both a technical and human challenge. Even before we leave the solar system, microgravity affects the human body. Bone density decreases, weakening the skeleton. Muscles atrophy without constant exercise. Fluid shifts affect vision and cardiovascular health. Immune system function declines. Traveling to other stars means extended exposure, potentially decades. Artificial gravity via rotation or acceleration may mitigate these effects. But building rotating spacecraft or sustaining high acceleration is engineering intensive and untested at this scale. Human survival is not guaranteed by will alone. Biology imposes hard limits. Moving a human or even robotic spacecraft to other stars demands immense energy. Chemical rockets cannot reach interstellar velocities. Nuclear fission, fusion, antimatter, or photon propulsion are theoretical solutions. The faster we want to go, the more energy is required, growing exponentially as we approach light speed. Generating, storing, and controlling these energies safely is a monumental challenge, demanding technologies far beyond what exists today. Even for robotic probes, energy efficiency is critical. Tiny deviations in velocity or fuel usage can delay arrival by decades. Even if humans survive the physical hazards, there is the human mind. Isolation from Earth, friends, and family. Limited social interactions within a small crew. Lack of sensory stimulation and monotonous environments. Decision-making under extreme uncertainty. Long-duration missions may require multi-generational crews, children born en route, advanced psychological training, AI companions, or virtual reality to maintain mental health. The stars demand resilience, patience, and adaptability as much as technology or engineering. In deep space, redundancy is essential. Systems must fail without catastrophe. Robots must repair themselves or each other. Humans must respond to emergencies without external help. History teaches that complex systems break under stress. Every interstellar mission must assume the possibility of failure and design accordingly. Multiple engines, life support systems, and communication channels, backup navigation instruments, stockpiles of consumables, contingency protocols for radiation storms, collisions, or equipment failures. Survival in interstellar space is not guaranteed. Preparation and foresight are essential. Human interstellar travel may be decades or centuries away, but robotic missions will test these challenges. Autonomous navigation systems, radiation shielding in deep space, long-duration life support for sensitive electronics, remote AI decision-making. Every probe sent beyond the solar system, from Voyager to breakthrough Starshot, lays the groundwork for future human missions. The risks humans face today can be simulated, mitigated, and learned from using robots. The dangers are immense. Radiation could kill, micrometeoroids could breach hulls, navigation errors could send travelers drifting forever, psychological stress could fracture crews, and yet humanity looks to the stars. Why? Survival. Expanding beyond Earth reduces existential risk. Knowledge. Understanding other worlds illuminates our own. Inspiration. The dream of interstellar travel unites generations. The universe does not yield to fear. Only those who prepare, innovate, and endure can hope to reach it. While interstellar human travel is distant, our solar system is the proving ground. Mars missions teach life support, radiation shielding, and isolation management. Lunar bases develop autonomous habitats and resource extraction. Asteroid exploration refines navigation, propulsion, and long-term mission planning. Each mission builds knowledge, technology, and experience. The obstacles of interstellar travel are not insurmountable. They are incremental challenges. Radiation mitigation becomes routine. Life support systems evolve into closed-loop, sustainable habitats. Propulsion improves from chemical to nuclear, ion, or laser-based systems. The stars remain far, but the path forward is visible. Every challenge in interstellar travel is formidable. Physics, biology, engineering, psychology, and energy all intersect. Cosmic rays and dust threaten life and electronics. Time dilation and relativistic physics redefine perception. Life support must function for decades or generations. Communication delays demand autonomy. Navigation errors can doom missions. Yet humanity has faced the impossible before. We have crossed oceans, reached the moon, and sent probes beyond the sun's influence. Interstellar travel is the next frontier. The obstacles are immense, the journey long, and the risks profound. But with preparation, innovation, and courage, humanity can confront the hazards of deep space and inch closer to the stars. The universe is vast, it is indifferent, and it waits. Every great leap begins with an idea, and every journey into the unknown begins with a ship. From the earliest canoes carved from wood to the spacecraft that orbited the moon, humans have always built vessels to carry them into new realms. Interstellar travel demands a ship unlike any we have ever imagined, a self-sufficient, durable, and adaptive machine capable of sustaining humans for decades, even centuries. In this section, we explore the concepts, technologies, and visionary engineering that could one day make humanity a multi-stellar species. The distances between stars are immense. Even at 20% of light speed, a journey to Proxima Centauri takes over 20 years. For more distant stars, voyages may span hundreds or thousands of years. This reality gives rise to the concept of the multi-generational ship, a vessel designed to sustain multiple generations of humans, self-contained ecosystems for food, water and oxygen, education and governance systems to maintain knowledge and culture, redundancy and repair systems to prevent mission failure over centuries. These ships are not merely vehicles, they are mobile civilizations. The crew must be prepared to solve problems that cannot be anticipated, maintain societal order, and adapt to evolving conditions. Life support is the linchpin of survival on long-duration missions. Water recycling. Every drop of water must be captured, purified, and reused. Oxygen generation, plants, electrolysis, and chemical systems must function continuously. Food production, hydroponics, aeroponics, and synthetic biology may provide nutrition indefinitely. Waste management. Efficient conversion of waste into usable resources is critical. NASA's experiments with the biosphere and ISS systems provide lessons. Microbes play a critical role in recycling nutrients. Genetic engineering may enhance plant growth and resilience in closed environments. Automation and AI can monitor systems, predict failures, and optimize efficiency. In a multi-generational ship, the ecosystem becomes a living, adaptive organism, as vital as propulsion itself. Traveling beyond the solar system requires propulsion far beyond chemical rockets. Fusion propulsion, fuses hydrogen isotopes to release massive amounts of energy, could achieve 10 to 20% of light speed. Challenges: controlled reaction, radiation shielding, and energy conversion. Annihilation of matter and antimatter releases energy at 100% efficiency, potential to approach relativistic speeds. Challenges: production, containment, and safe throttling. Uses solar or laser-driven photons to accelerate a craft, extremely efficient, no onboard fuel required. Challenges: maintaining alignment, large-scale laser infrastructure, and sail integrity. Bussard ramjets collect interstellar hydrogen for fusion, warp drives, theoretical space-time manipulation to bypass the light-speed barrier. While currently speculative, these ideas illustrate humanity's imagination and potential future breakthroughs. Interstellar travel is not only about propulsion, it is about survival, radiation, galactic cosmic rays, solar particles, and secondary radiation, micrometeoroids. Tiny particles moving at relativistic speeds can puncture the hull. Temperature extremes, cold of interstellar space versus heat from onboard systems. Potential solutions include magnetic or plasma shields, deflect charged particles away from the ship, layered hulls, sacrificial layers to absorb micrometeoroid impacts, water or ice barriers, absorb radiation while providing resources for life support. Shielding must balance protection and mass, as heavier ships are harder to accelerate. A multi-generational ship requires continuous energy for propulsion, life support, radiation shielding, communication, AI, and robotics. Potential sources: nuclear fission, fusion, compact and reliable, antimatter, immense energy density, if containment is possible, solar arrays, useful near stars but limited in interstellar space, stored chemical or advanced batteries, supplementary power, advanced reactors capable of producing gigawatts continuously for decades may be humanity's first true starship engines. Energy management is mission critical. Failure is not an option. Decades of microgravity cause muscle atrophy, bone density loss, cardiovascular deterioration, visual impairment, and fluid redistribution. Artificial gravity can be generated via rotating habitats. Centrifugal force mimics gravity. Linear acceleration. Sustained thrust creates a force equivalent to gravity. Rotation introduces engineering challenges. Structural integrity over large radii. Coriolis effects that affect movement. Material fatigue over decades. Artificial gravity is not a luxury. It is essential for long-term human survival in interstellar space. Even small errors in trajectory amplify over light years. Star positions shift due to proper motion. Gravitational influences from unseen objects can alter paths. Interstellar dust clouds obscure instruments. Future starships may use pulsar navigation, using precise signals from rotating neutron stars. Autonomous AI systems, detecting deviations and correcting course. Onboard star mapping, continuously updating positions and trajectories. Navigation must be self-contained and independent, as communication delays with Earth span years. Even at the speed of light, signals take years to travel. Earth to Proxima Centauri, 424 years one way. Earth to Alpha Centauri, 437 years one way. Farther stars, decades, centuries, or millennia. Implications: crews cannot rely on real-time instructions. AI and decision-making autonomy are mandatory. Psychological impact: isolation from human society. Communication is not simply technical, it is a social and emotional barrier for interstellar travelers. Humans cannot survive purely as individuals in isolation for decades. Multi-generational crews require governance systems. Education ensures that knowledge, skills, and culture persist. Conflict resolution mechanisms are critical to maintain order. Potential strategies: rotating leadership and shared responsibilities. Structured education from childhood to adulthood. Cultural continuity through storytelling, art, and ritual. A starship becomes a miniature civilization. with social engineering as critical as engineering for propulsion or shielding. Interstellar ships must be self-repairing. AI-assisted robotics for maintenance, redundant life support and propulsion systems, 3D printing or in-situ manufacturing for replacement parts. Even minor failures can cascade into catastrophe. The longer the journey, the greater the need for resilience, foresight, and autonomous problem-solving. Before humans venture, robotic explorers test technologies and paths, microprobes at 20% light speed, autonomous AI handling navigation, propulsion, and data collection, radiation-hardened electronics testing shield designs. Robots provide proof of concept, reducing risk for eventual human missions and mapping hazards of interstellar space. Potential mission profiles: near-future mission, 10 to 20% light speed, robotic or multi-generational, mid-future mission, fusion or antimatter propulsion, human crew, decades of travel, far-future mission, exotic propulsion, warp drives, interstellar colonization, centuries-long journeys. Each requires advances in energy generation, propulsion, life support, shielding, governance, and social structure. Every step forward builds the foundation for the next leap. Interstellar travel is not merely technical, it is moral. Sending humans on decades-long missions involves consent across generations. Multi-generational crews may face ethical dilemmas regarding reproduction, resource allocation, and survival priorities. AI autonomy raises questions about decision-making and risk assessment. Exploring the stars forces humanity to confront the ethics of survival, autonomy, and civilization. The challenges are immense, yet humanity persists. Curiosity drives exploration. Survival motivates expansion beyond a single planet. Technological innovation transforms obstacles into possibilities. Every plan, simulation, and mission brings us closer to touching the stars, not as dreamers, but as engineers, scientists, and pioneers. The interstellar ship is more than a machine. It is a statement of intent. It embodies human ingenuity, adaptability, and courage. It preserves life, knowledge, and culture across decades or centuries. It confronts the physical, biological, and social challenges of space. The architecture of the future requires vision, ambition, and collaboration on a planetary scale. Every innovation, every experiment, every probe sent beyond the solar system is a step toward turning humanity into a species capable of surviving among the stars. The journey will be long, the risks will be high, the obstacles will be formidable. But the universe awaits, and humanity's reach is far from its limit. Every civilization that has gazed upward has asked the same question: how long before we leave the confines of our home world? The moon was once a dream. Mars was once a distant possibility. Now, humanity contemplates traveling to other stars, a leap that stretches imagination, technology, and patience. The journey is not only measured in kilometers or light years, but in decades, centuries, and generations of effort. Long before humans set foot beyond the heliosphere, robotic explorers paved the way. The Voyager spacecraft, launched in 1977, became humanity's first emissary beyond the solar system. Traveling at roughly 17 kilometers per second, it has already crossed into interstellar space. New Horizons journeyed to Pluto and beyond, providing crucial data on the Kuiper Belt. These early missions demonstrate navigation over billions of kilometers, communication delays spanning hours, operation in extreme radiation and temperature conditions. Future robotic missions will be far faster, far more capable. Breakthrough Starshot envisions tiny light sail probes accelerating to 20% of light speed, reaching Alpha Centauri in roughly 20 years. These microprobes must withstand radiation, interstellar dust, and the extreme demands of autonomous operation. Robotic missions serve as technological proving grounds, testing propulsion, shielding, navigation, and communication for eventual human travelers. Robots can go fast, but humans require life support, protection, and long-term planning. Two broad approaches emerge. Entire communities live, work, and reproduce aboard a ship. Multi-generational journeys spanning decades to centuries. Education, culture, and governance must be maintained over lifetimes. Challenges include psychological resilience over decades, resource recycling with near-perfect efficiency, social cohesion, and conflict resolution. Future propulsion could allow humans to travel at significant fractions of light speed, reaching nearby stars within a single human lifespan. Time dilation could reduce perceived travel time for passengers, requires unprecedented energy, shielding, and navigation systems. Both approaches demand a combination of engineering, biology, and social science, illustrating that interstellar travel is as much about humans as machines. Interstellar travel is measured not in years, but in epochs. Near future, next 50 years. Robotic probes leaving the solar system, testing light sails, ion drives, and fusion propulsion. Mid-future, 50-200 years. First human missions to Mars, asteroids, and perhaps the outer planets. Preparation for long-duration interstellar voyages. Far future, 200+ years. Multi-generational ships traveling to the nearest stars. Distant future, millennia. Civilization capable of interstellar colonization, seeding life on exoplanets and spreading across multiple star systems. The timeline underscores patience. Humanity must build incrementally, learning from each mission, refining technology, and preparing future generations for challenges beyond imagination. The contrast is stark. Can survive extreme radiation and microgravity, require minimal life support, can travel faster and farther with smaller mass, cannot make ethical or creative decisions beyond programming, adaptable, creative, and capable of problem solving, require extensive life support, shielding, and psychological care, limited by lifespan and biology, carry culture, knowledge, and vision. The strategic choice is not either or, but both and. Robots first, humans later. Robotic scouts prepare pathways, map hazards, and test propulsion. Humans follow once safety, energy, and sustainability can be ensured. This combination reduces risk and maximizes the chances of success. Interstellar missions have different goals. Exploration gathers data, maps stellar systems, and tests technology. Colonization establishes permanent human presence on exoplanets. Exploration informs colonization. Robotic probes detect planets with habitable zones, water, and resources. Observations guide mission planning, energy requirements, and social structures. Colonization requires self-sufficiency, including closed-loop ecosystems, sustainable energy sources, resource extraction from planets, moons or asteroids, long-term governance and culture maintenance. A mission without preparation risks decades of failure, lost lives or stranded crews. Human interstellar travel hinges on propulsion. Chemical rockets, only suitable for solar system exploration. Nuclear fission, fusion, feasible for high-speed, long-duration missions in the next century. Antimatter propulsion could enable near-light-speed travel, centuries away in development, laser-pushed light sails. Scalable for robotic probes, but human-scale missions require enormous infrastructure. Speculative drives, warp drives, or space-time manipulation remain theoretical. Each propulsion type has distinct timelines, energy needs, and technical challenges, shaping the roadmap for interstellar exploration. Decades or centuries of confinement demand careful attention. Maintaining mental health through work, recreation, and social interaction. Preventing social collapse or authoritarian rule in closed systems. Education systems that preserve knowledge across generations. Multi-generational decision-making that balances survival with mission goals. Space becomes not only a physical frontier, but a human frontier, testing civilization itself. Sustaining multi-decade or century-long missions demands unprecedented energy solutions. Onboard reactors for propulsion and life support. redundant energy storage to survive failures, harvesting resources from interstellar medium, hydrogen, asteroids, etc. Renewable energy cycles for closed-loop systems. Energy is the lifeblood of any interstellar mission, dictating speed, survival, and flexibility. A speculative roadmap, 2020-2050. Robotic probes leaving the solar system, testing propulsion, shielding, and AI autonomy. 2050-2100. First Mars and outer planet missions, development of artificial gravity and life support systems. 2100-2200. Fusion-powered ships tested in the outer solar system, multi-year human missions. 2200-2300. Light-speed fraction missions to Alpha Centauri, using advanced shielding and AI guidance. 2300 plus. Multi-generational human colonization of nearby exoplanets, establishing off-world civilization. Each milestone builds technological, social, and cultural capital for the next leap. Time delays force autonomy. A starship traveling to Proxima Centauri cannot rely on Earth for real-time support. AI systems, humans, and robotic assistants must make life or death decisions independently. Social structures must endure isolation and maintain continuity. Interstellar missions are tests of human civilization itself, exploring whether a society can survive beyond Earth's cradle. Choosing a destination is crucial. Exoplanet discovery has revealed thousands of candidates. Factors include distance, habitability, resource availability, and stability of the star system. Robotic surveys refine targeting, reducing risk for human travelers. Even then, unknown hazards remain. Planetary atmospheres may be hostile. Gravity, radiation, and weather may challenge colonization. Resource scarcity could threaten survival. Preparation, reconnaissance, and adaptation are essential. Interstellar missions raise profound ethical questions. Can future generations consent to lives predetermined before their birth? How do we balance survival, exploration, and autonomy on a multi-generational ship? Who decides priorities in life or death situations decades from now? These questions force us to reflect on civilization's values, not just engineering capabilities. Long-term strategies for interstellar survival include distributed civilization. Multiple ships, planets, and habitats reduce existential risk, genetic and cultural continuity, ensuring humans maintain knowledge and adaptability. Autonomous AI, guardians of knowledge, repair, and mission objectives. Interstellar communication networks, maintaining some connection across light years. These strategies envision humanity as a cosmic species, not confined to a single world. Every human endeavor teaches lessons for interstellar travel. Long sea voyages in the age of exploration relied on redundancy, navigation, and social cohesion. Early colonies adapted or failed depending on preparation, leadership, and resource management. Space travel mirrors history. Careful planning, incremental testing, and adaptation to unforeseen hazards are essential. History reminds us, ambition without preparation is catastrophic, but vision with discipline can conquer the impossible. The timeline for interstellar travel is measured in centuries and millennia. Robots will lead the first voyages, mapping the void and testing new technologies. Humans will follow, either at high speed or through multi-generational missions. Civilization will need to adapt, innovate, and persevere in ways never required before. Every mission is a lesson in endurance, innovation, and courage. Every light year traveled is a step toward making humanity a species capable of surviving among the stars. The stars are distant. The challenges are immense. The journey is long. And yet, the universe waits. Humanity's arc toward the stars has only just begun.